Welcome to tonight's video on Unit 2, Part 1. We'll talk about limits of sequences. The first thing we need to talk about is what type of sequence you can have when you're talking about the limit. And the limit is a concept. Limit is a concept where basically you're asking yourself, where does the number reach? Like, it doesn't have to equal that, but what is the function going towards? And I gave an example in class of, hold on. Gave an example in class, if you drew a line, and let's say, here's the x and y axis. So here's x equals a. And these two people are on that line going towards x equals a. All right, so basically, you know, because that's a whole, that you can't equal a. And let's say this is y equals 3. But what you're saying when you say the limit as x approaches a of the function is what number is the function going towards. And in this case, it's approaching 3. Even though it might not equal 3, they're getting close to 3. And that's what it means to be the limit of a function. There are two types of sequences. One which is called convergent, where it's a sequence that is going towards a specific number, all right, where the number that the limit is a real number. And there's what's called a divergent sequence, and that's basically where the limit does not exist. Because remember, infinity is not a real number. It is a term. It means that it's getting greater or smaller. So the rules for real numbers do not apply to infinity. So there's three reasons that the limits do not exist. The first one is what's called unbounded behavior. The limit approaches infinity or negative infinity. The second reason is what's called oscillating behavior. It's one where the sequence goes between two values. And then the third one is that the limit from the left does not equal the limit from the right. And we'll discuss that one in a future unit. So, methods for finding a limit. There are 5 methods that we'll talk about. The first one is what's called observing terms. So when we look at a function like this, we want to observe the pattern in the terms. So to help yourself, you might want to use your calculator. The function was, so hit y equals, and the function was a fraction. So we're going to put parentheses. So it's 4 minus, and then it's pi n to the third, so we're going to say x to the third, divided by, and then it's x minus 6x to the third plus 1. And then we gotta hit enter. All right, so now what we want to do is we want to look at the table, and remember, you're gonna hit second function, table set. And now you want to make sure that the independent variable you ask it asks you what you want to put in. The other things don't matter, but just that. So then go second function table, and yours will be blank. It'll allow you to put numbers in. So yours will look something like this. So you're going to put numbers in like 1. So when you put 1 in, you get that. You can put 2, and then put like 10, and then put like 100, and then put 1,000. So you get the idea that as you put bigger numbers in, like 1,000,000, notice you get 0.5236. So by observing terms, by saying, okay, yeah, the first term was negative 0.215, the second term was 0.4696, and then we went to 0.5239, and then we went down the line to 0.5236. So the limit as n approaches infinity of this function is 0.5236. So we can do the same thing for the next one. So if we put in numbers, and I'm not going to show the calculator, but if you put in numbers for 3 to the n, you get 3, 9, 27, 81, 243, and then notice it just keeps getting bigger. So the limit as n approaches infinity for this function, well, it would be infinity, which means it does not exist because it's unbounded behavior, meaning it's going to go up and up and up forever and ever. The next one, if we put in the terms, and you can do it on your calculator, you put in 1/2, 2/3, 3/4, 4/5. So you notice a pattern, like it's going to get to 99 over 100, and then it's going to get to like 999 over 1,000. So basically it's getting close to the number 1, but it's not going to reach there, but it's getting so close that that's what the limit is. It's 1. The next one, 3 over 2 to the n. So think about if n is 1, it's 3/2, then 3/4, then 3/8, 3/16, 3/32, 3/64. So notice it's getting smaller and smaller and smaller. So as you put bigger numbers in for n, the fraction is basically going to become 0. It's going to become so small it doesn't count. The second way that we can find the limit is by plugging in infinity wherever you see an n. So the limit as n approaches infinity of this function here. So what I'm going to do is I'm going to put infinities in for the n's. So this limit for 5 is 5, but 1 over infinity, well, as this number gets bigger and bigger and bigger, the fraction gets smaller, so it's basically 0. So 5 minus 0 is still 5. So for this function here, the limit as b sub n equals 3 to the n as it goes to infinity of 3 sub to the nth power. Well, 3 to the infinite power is equal to infinity, which means it does not exist because it's unbounded behavior. For part C, first thing I want to do here, finding the limit as n approaches infinity of n squared over n plus 1 minus n squared over n plus 2 is to put the infinities in. So it's infinity squared over infinity plus 1 minus infinity squared over infinity plus 2. which is, sorry, move it that way, which is infinity over infinity minus infinity over infinity. Well, infinity over infinity is what we call indeterminate, meaning we can't determine the answer. So right now we'll put question marks because we haven't talked about what it means to be indeterminate, but we'll come back to this as a result. But basically it's indeterminate because infinity is not a number, so subtracting the same thing does not necessarily get you 0. It's a term, so the rules for that do not apply as they would for real numbers. For the next one, the limit as n approaches infinity of n squared plus n, so it's infinity squared plus infinity, which means it's just going to get bigger. It's infinity, which means it does not exist because of unbounded behavior. All right, before we go on to rules 3, 4, and 5, or ways to find limits numbers 3, 4, and 5, there are some rules that we need to talk about. The constant product rule means it's like the limit as n approaches infinity of 5n would equal 5 times the limit as n approaches infinity of n. If you add the sum and difference of a limit, so for example, the limit as n approaches infinity of n plus 5 would equal the limit as n approaches infinity of n plus the limit as n approaches infinity of 5. And then the same thing could be said for the product rule. If you had the limit as n approaches infinity of, we'll say, n plus 5 times n plus 2, we could say it's the limit as n approaches infinity of n plus 5 times the limit as n approaches infinity of n plus 2. So it would be the product of those limits. For the quotient rule, the limit as n approaches infinity of n plus 2 over n plus 1 would be equal to the limit as n approaches infinity of n plus 2 divided by the limit as n approaches infinity of n plus 1. So then we've talked about the harmonic sequence, where if the limit as n approaches infinity of 1 over n to a power is equal to 0, and then the constant rule, like the limit as n approaches infinity of 5 is equal to 5. So the limit of any constant as n approaches infinity is just that constant. These two are going to be the basis for our next rule, trying to get every limit to be in this form using the other rules. And we'll talk about that in the next video. All right, hope you had a good evening. I will see you in class.